Students, I hope you're doing fine. So today we will solve some more examples regarding the rotation about a fixed axis in our dynamics book. This is chapter 16, right? So dynamics, or we were actually discussing kinematics of a rigid body. So this is section 3 in this chapter, rotation about a fixed axis. So we'll be solving, as I said, several new examples today, starting with problem 1620. So here, the problem says that we have a motor. So this motor, or A, or the motor at A, I guess, yeah. So a motor gives gear A an angular acceleration of alpha A equals 4t cubed radians per second squared. Now, the first important information here that we need to understand is that the acceleration is not constant and it is time dependent. As the time increases, then the angular acceleration of gear A would also increase. Now, if this gear is initially turning at initial velocity, angular velocity of 20 radians per second. So omega A, the initial one, is 20 radians per second. So now we need to determine the angular velocity of gear B at time equals 2 seconds. So how do you solve these problems? As you see, guys, this gear at A is attached to an engine or some kind of a motor, and this motor is causing the rotation of this gear. Now, see here, we have a mesh point between gear A and gear B here. Now, the important information that we understand from this mesh point is that the tangential acceleration as well as the velocity at this point are equal. So the tangential velocity of gear A and gear B are equal, and the tangential accelerations of gear A and gear B are also equal. So also, if we have information here and we need to move to another point, then we have to solve for unknowns here first and then move to the other gear or to the other part of the machine. So let's just write down whatever we know now and start solving the problem. So in this problem, we know the following. We know that at gear A, the angular acceleration equals to 4t cubed radians per second squared. We also know that the angular velocity at gear A, or the initial one, the initial angular velocity is equal to 20 radians, 20 radians per second. This is when the time is equal to 0, because it's the initial velocity. Now the question is asking for the following. What is the angular velocity of gear B at time of 2 seconds? Okay? So, now the first important information we were given is the angular acceleration at gear A. Now, this isn't constant. That means it's changing with time. Now, the first equation that we need to use, or how do we think about this problem? We said that we have two gears here. I'm drawing them as if they were pulleys. Anyways, I'm sorry, these are gears. So if this gear is rotating, then it will cause the other gear to rotate as well. So if gear A was rotating clockwise, then gear B would be rotating counterclockwise, right? Now, this movement of gear A would cause the movement of gear B. At this exact point, we know for a fact that the velocity of gear A, which is the tangential velocity, right, is equal to the velocity of gear B. Okay, so now we have to move from here to here, from A to B. So we need to work with A and start finding unknowns in A. So, okay, let's just write whatever we know from here. So we know that the tangential velocity basically is equal to the angular velocity multiplied by the radius. So this is for A. This should equal the same thing in B. Omega multiplied by r of b. So now we don't know omega a, but we know alpha a, right? So if we integrate, we will get the value of omega a. Multiply that by r, and then here, so we would know everything here, and then we know r already, rb, it's known. We just need to find omega b. That's it. So this is the idea. So we know for a fact that the angular acceleration is related to the angular velocity using this equation, which is basically the first derivative of the angular velocity with respect to time. So now if we separate variables, we're looking for omega. So we get d omega equals alpha dt. Now we have to integrate between limits, the initial angular velocity and the final one, and here between 0 and the final time. Carry out your integration, you get omega minus omega naught, which is the final omega minus the initial omega, equals t to the power 4. Hence, the final omega equals t to the power 4 plus the initial omega. And this is the equation that we need to work with. But remember, here we're talking about gear A. Here we are talking about gear A. So this is for gear A. Alright, now we need to find the final velocity or angular velocity at a time of 2 seconds. So here, just substitute t as 2 to the power 4 plus w, which is 20, and here you get, I guess, 36 radians per second. Substitute these values in this equation. We know that omega now is 36 radians per second multiplied by the radius. The radius of gear A, let's just go back and check the radius. So the radius of gear A is 0.05 meters, which is 50 millimeters, right? 50 millimeters, and here it's 150 for B. 50 and 150. So anyways. But this is radians per second, doesn't really matter. We're looking for this, this omega. So this is 50 millimeters equals omega b multiplied by 150. So immediately we would know that the angular acceleration of gear B at a time of definitely 2 seconds, right? 2 seconds at a time of 2 seconds. So it was asking us to find this at time of 2 seconds, right? At a time of 2 seconds equal to 12 radians per second. That's it. Very simple, easy, and straightforward. Just remember that at the mesh point, always these values are similar. Also, the angular acceleration at, the tangential acceleration, at at A is equal to tangential acceleration of gear B. However, remember, only the tangential. The normal ones are not equal for A and B. These are not equal, but these are definitely the tangential ones are equal, whether we were talking about acceleration or velocity. Okay, that's it, I guess. Thank you very much.